Before we can multiplex voice channels onto a digital link, we first need to convert analog voice into digital form. Human voice is a continuous analog signal in the range of 0 to 4 kHz. Digital communication, however, uses discrete bits, zeros and ones. So we need a way to convert between the two. Analog to digital conversion is done by sampling the sound wave and representing each sample as a number. According to the Nyquist sampling theorem, we need at least twice the maximum frequency to perfectly reconstruct the signal. For voice at 4 kHz, that means 2 times 4000 equals 8000 samples per second. The most common method for encoding these samples is called PCM, pulse code modulation. In PCM, each sample is quantized into one of 256 levels, which requires 8 bits per sample. So the bitrate for one voice channel is 8000 samples per second times 8 bits per sample, which equals 64 kilobits per second. This 64 kilobits per second is the fundamental building block of digital telephony. It is called a DS0 channel. PCM remains the foundation of voice digitization today, and even modern voice-over IP systems use PCM or its compressed variants like G711 and G729. Now that we have digital voice channels at 64 kilobits per second each, how do we send many of them over a single transmission line? Installing a separate line for every channel is clearly not practical. The solution is multiplexing, sending many channels over one line. Time division multiplexing, or TDM, achieves this by giving each channel a fixed time slot. The multiplexer takes 1 byte 8 bits from each channel in sequence and sends them one after another on the output line. After collecting 1 byte from every channel, it starts over with the next byte. This is called byte interleaving. .RT, for example, with 32 channels, each at 64 kilobits per second, the output rate must be at least 32 times 64, which equals 2048 kilobits per second, or about 2 megabits per second. The multiplexer has only 1 over 8000 seconds, that is 125 microseconds, to collect and send 1 byte from all 32 channels before the next sample arrives. But how does the receiving end know which byte belongs to which channel? This is solved by synchronization. Special synchronization bits are inserted into the frame to mark where each group of 32 bytes begins. The demultiplexer reads these sync bits and distributes the following bytes to the correct channels. Different regions of the world develop their own TDM carrier standards. All three start with the same basic channel rate of 64 kilobits per second, but they differ in how channels are grouped. The European standard, called SEPT or E-carrier, uses E1 as its first level. E1 has 32 channels, 34 user data, and 2 for frame synchronization and signaling, giving a total rate of 2.048 megabits per second. The North American standard, called T-carrier, uses T1 or DS1 as its first level. T1 has 24 user channels plus 8 kilobits per second for signaling, giving 1.544 megabits per second. The Japanese J-carrier mirrors T1 at 1.544 megabits per second with 24 channels. These first-level signals are then multiplexed into higher levels. E2 XOR E1 streams into 8.448 megabits per second with 120 channels. E3 reaches 34.368 megabits per second with 480 channels. E4 carries 139.264 megabits per second with 1920 channels, and E5 reaches 565.148 megabits per second with 7,680 channels. Although all three systems share the same 64 kilobits per second base rate, they are incompatible with each other due to different framing and encoding methods. Let us work through 2 examples to solidify the PCM calculation. Example 1. Digitizing a standard telephone voice channel. We start with the voice bandwidth of 4 kHz. Applying the Nyquist theorem, The sampling rate is 2 times 4000 Hz, which equals 8000 samples per second. With PCM using 8 bits per sample for 256 quantization levels, the bitrate is 8000 times 8, which equals 64,000 bits per second or 64 kilobits per second. This is one DS0 channel, the standard digital voice rate. Example 2. Digitizing a commercial television signal. A TV video signal has a bandwidth of about 6 MHz. The sampling rate will be 2 times 6 million, which equals 12 million samples per second. If we use 8 bits per sample, the bitrate is 12 million times 8, which equals 96 megabits per second. With 10 bits per sample for higher quality, it becomes 120 megabits per second. This is equivalent to an E4 carrier. A single television channel requires the capacity of 1920 voice channels. Let us review. PCM pulse code modulation converts analog voice to digital by sampling at 8000 times per second and encoding each sample with 8 bits, producing the standard 64 kilobits per second voice channel. TDM time division multiplexing combines multiple 64 kilobits per second channels by interleaving 1 byte from each channel in sequence. Synchronization bits mark frame boundaries so the receiver knows which byte belongs to which channel. 3 carrier standards exist. E-carrier in Europe with 3, 2-channel E, 1 at 2.048 megabits per second, T-carrier in North America with 2, 4-channel T, 1 at 1.544 megabits per second, and J-carrier in Japan. These hierarchies scale up to thousands of channels at hundreds of megabits per second. In the next lesson, we will cover frequency division multiplexing, statistical multiplexing, and wavelength division multiplexing for fiber optics.